Nice. We'll go to the next talk, indeed, from the team of Umberto in Torino. And the talk will be presented by Karol and Valentina. Karol and Valentina, they are working with Umberto, and they spent some time here in Bordeaux, and we hope that maybe Ludovica can spend some time in Torino to work with you. Let's see. Please.
Okay. Okay. Good afternoon, everybody. Can you see my screen?
Everything is fine.
Okay. So my name is, thank you, Angelo, for the introduction. My name is Karol Calò, and I am a PhD, a post-PhD, postdoctoral researcher at Politecnico di Torino with Umberto's group. So me and my colleague Valentina Mazzi will be present you an overview of some advanced tools of analysis for in silico characterization of near wall and intravascular hemodynamics in abdominal aortic aneurysms. So as we've already seen from the presentation of Floriana and Ludovica, the abdominal aortic aneurysm, also known as triple A, is a pathological condition consisting in an irreversible enlargement greater than 3 centimeters of the abdominal aortic wall, usually in the infrarenal portion. So the development of wall enlargement is caused by a progressive mechanical weakening of the vascular walls, mainly due to elastin and collagen fibers degradation. The onset and progression of the aneurysmatic disease is still unclear. However, it is widely accepted, the hypothesis that the triple A's pathogenesis is mainly influenced by different risk factors, for example, systemic risk factors such as age, gender, genetics, hypertension, and also biomechanical factors, in particular hemodynamic forces like pressure and shear stresses. One of the main risks related to abdominal aortic aneurysms, as we've already seen, is the formation of the intraluminal thrombus, ILT, while the most catastrophic complication, of course, is aneurysm rupture with consequent death. So the current clinical standards, again, are mainly for the treatment of the abdominal aortic aneurysm are mainly based on the aneurysm size and also growth rate. And in particular, according to the guidelines, an aneurysm surgical treatment is suggested for those aneurysms with a diameter greater than 5.5 centimeters or with a growth rate greater than 1 centimeter per year. So, as I previously said, among the biomechanical risk factors involved in the pathogenesis of the abdominal aortic aneurysm, hemodynamics plays a key role. But why? First of all, because because various vascular diseases, in particular aneurysm, tend to preferentially develop where blood flow patterns are most complex and intricate. But besides being involved in the causes of aneurysmatic disease, hemodynamic forces may also induce thrombus formation and growth, and also aneurysm rupture. So for all these reasons have led to formulate the so-called hemodynamic hypothesis, according to which there is a localizing hemodynamic risk factor for vascular disease, which is characterized by a strong and complex interplay between vascular geometry, wall shear stress, and intravascular flow. Wall shear stress is probably the hemodynamic factor most widely involved in blood vessel disease. It is defined as the tangential force per unit area exerted by flowing blood on the endothelial lining covering the intima surface of the vascular wall. So, endothelial cells are constantly exposed to the action of the wall shear stress, and they are able to translate the mechanical stimuli into intracellular signals, which can modulate their structure, morphology, and functions. And so in the presence of aggravating flow events, wall shear stress may trigger an abnormal biological responses, such as endothelial cells dysfunction or injury, an increased permeability of the vascular wall, and above all, the platelets activation, aggregation, and deposition, which are known to be responsible for the thrombotic disease. Okay, so besides the shear stress exerted on the vascular wall, also the organization of blood flow patterns inside the lumen, inside the bulk, has a strong impact on the vascular disease progression, in particular on the aneurysmatic disease. In fact, for example, flow recirculation has been found to be positively correlated with the biomarkers of thrombosis. And also the presence and organization of vertical structures affect platelet dynamics. In particular, some studies have found that first, the platelets are trapped inside the vertical structures, and then due to vortex mixing, they are transferred and activated at sites of high shear stress. And finally, when the vortex breaks up, it releases the activated particle platelets, which can either aggregate and adhere near the vascular wall, or also circulate to the systemic, enter the systemic circulation, and then also, for example, cause other complications such as lower limb thrombosis. Finally, also helical flow, which is well known to be a typical feature of arterial flow, plays a beneficial role in suppressing flow reversal and flow recirculation, and subsequently reducing platelet adhesion and thrombotic risk. So for all these reasons, and given, of course, the strong impact that the aneurysmatic disease, but in general vascular disease, has on our society, it is necessary to gather knowledge of vascular pathophysiology by deeply understanding local hemodynamics. And so to do so, the personalized computational fluid dynamics represents currently the most powerful tool to model blood flow in silico. CFD integrated by clinical imaging allows for a realistic reproduction of arterial vessels fluid dynamics. In fact, clinical data are used to reconstruct the real geometry of the vessel, and also to provide personalized boundary conditions to solve the fundamental fluid mechanics Navier-Stokes equations using numerical approaches based, for example, on finite volume or finite element methods for the Navier-Stokes equations discretization. Then as the output of the personalized computational fluid dynamics, which is of course the solution of the Navier-Stokes equations, is used to perform an advanced post-processing of the simulation results, and to provide a characterization of arterial hemodynamics, both in terms of wall shear stress and derived parameters, and also in terms of intravascular quantities. So, the study that we present was motivated by the need to characterize local hemodynamics in an abdominal aortic aneurysms in order to better understand the risk associated with the aneurysm onset and progression. And so The aim of this presentation is to provide an overview of some advanced tools of analysis for the hemodynamic characterization of personalized CFD models of abdominal aortic aneurysm, able to capture the main feature of aneurysm hemodynamics, which will be ultimately useful to identify more accurate clinical markers for AAA risk prediction. Okay, so going to the methods, this slide shows the data set of 8 patient-specific models of abdominal aortic aneurysm, which Florian teams at Nuria provided us. And as you can see, this data set is characterized by a large geometrical intervariability in terms of aneurysm shape. This workflow shows the main steps that we performed in our study. So first of all, the first step is the lumen segmentation from CT scans. And in particular, the segmentation was performed automatically by Florian's group at Nuria. And for this study, we focused on the infrarenal portion between the renal and the iliac bifurcations. Then a smoothing step was applied to the raw segmented vessel in order to prepare the surface for the mesh generation. Then we searched the literature for the boundary conditions to be applied to the inlet and outlet sections of our model, and then we proceed to perform the unsteady, the transient CFD simulations using an open source code based on finite element method. And the final step, which is the one that we will be discussing more in detail in our presentation, is the post-processing, which of course focuses on the characterization of the hemodynamics inside the abdominal aortic aneurysm, both in terms of near wall and intravascular flow.
Okay, so to characterize the near wall flow topology, first, we analyzed the canonical near-wall hemodynamic descriptors. So starting from the washer stress data from the CFD simulations. So first, we computed the time average washer stress magnitude, as the exposure to low washer stress is widely recognized as a marker of disturbed flow and promoter of vascular disease. In particular, in studying the hemodynamics in abdominal aortic aneurysm, it has been proposed that platelets activate in region of high shear and then accumulate in region of low shear stress. So going to results, we can see the time average washer stress distribution on the luminous surface of models. And we can observe that the expansion regions of models are characterized by low time average washer stress value. In particular, model 7, presenting a marked expansion region, is characterized by the lower values of washer stress. Then we computed another canonical washer stress-based metric, the oscillatory shear index. This index identifies regions on the luminous surface where instantaneous washer stress vector deviates from the main flow direction in a large fraction of cardiac cycle. Regions on the luminous surface exposed to high values of OSI are typically associated with bifurcation flow or vortex formation on local flow reversal, known to be promoting factor for vascular disease. So going to results, from the distribution of the OSI on the luminous surface, it emerged that the high value of OSI were located on the aneurysm sac and close to the neck region, reflecting the intricate hemodynamics characterizing these regions. So now I briefly introduce a new advanced tool of analysis for the characterization of the local hemodynamics. the Washer stress topological skeleton. So based on dynamical system theory, the topological skeleton of the Washer stress vector is composed by a fixed point, a point where the vector field vanishes, and their connection, called manifold, that are contraction and expansion regions linking the fixed points. So the interest in the Washer stress topological skeleton arises from its ability to reflect the cardiovascular flow complexity and the presence of near wall hemodynamic features associated with vascular disease. Very recent findings have suggested a strong link between Washer stress topological skeleton features and adverse vascular response. In particular, it has been demonstrated that the Washer stress topological skeleton can be useful to provide a template of near-wall mass transfer in a patient-specific computational hemodynamics model of coronary artery. That Washer stress topological skeleton predicts long-term restenosis risk after surgery in carotid bifurcation, the ability to predict the temporal changes in coronary arteries wall thickness in an atherosclerotic peak follow-up study, and moreover, the ability to predict future myocardial infarction in coronary artery. So the analysis of the Washer stress topological skeleton can be performed by using Lagrangian-based technique. Lagrangian approaches are useful to characterize the global organization of the vector and its evolution over time. However, Lagrangian-based methods are computationally expensive and time-consuming. Recently, our research group proposed a Eulerian method to analyze the Washer stress topological skeleton. The Eulerian-based approach has a simple definition, making its implementation easy and characterized by a reduced computational cost. So, Lagrangian approach to analyze the topological skeleton of Washer stress vector is performed by seeding the domain of interest with tracer particles and by visualizing their motion. The aim of this approach is to detect coherent features describing how the flow is organized. Such a Washer stress coherent structure can be traced out from numerical integration of particles based on the near wall buffer velocity. Here we show an explanatory example with the initial distribution of the particles, the position of particles after one cardiac cycle, and the position of particles after two cardiac cycles. And we can observe that particles are attracted to a Washer stress coherent structure. Moreover, from Lagrangian processing of Washer stress data, we can compute the Washer stress exposure time to quantify the amount of time that particles spent near the wall. Then the Eulerian approach to analyze the topological skeleton Washer stress is based on the Washer stress divergence. So, starting from the Washer stress data on the luminal surface, we identified Washer stress manifolds by computing the divergence of the normalized Washer stress vector. In particular, regions characterized by negative values of normalized Washer stress divergence identify contraction regions, while regions characterized by positive values of normalized Washer stress divergence identify expansion regions. Then, to identify Washer stress fixed points, we computed the Poincaré index. And finally, we classified the fixed points by computing the eigenvalues of the Jacobian matrix. Finally, we obtained the complete Washer stress topological skeleton. So, going to results, first we applied the Washer stress divergence-based method to the cycle average Washer stress vector to identify the main integral features. We can observe the presence of a contraction region at the proximal part of the neck where the flow entered in the expansion regions of the model. In addition, we computed the topological shear variation index to quantify the variation in the washer stress contraction and expansion action exerted at the luminal surface along the cardiac cycle. From the results, we can observe that the expansion regions of the model, the aneurysm sac, are characterized by high TSVI values. The model 2 and 8, where probably the thrombus formation are led to a physiological blood canalization, are characterized by a different TSVI distribution, with a large part of the model characterized by low TSVI values. So finally, we computed the fixed point weight and residence time, RT-nibla, to quantify the fraction of cardiac cycle spent by fixed point at a specific location on the luminal surface, weighted by the washer stress divergence to measure the local contraction and expansion action. The analysis of the luminal surface distribution of fixed point weight and residence time highlighted the presence of a region at the aneurysm sac and close to the neck, where instantaneous washer stress fixed points appear and reside for a longer fraction of cardiac cycle. So, to investigate the link between washer stress topological skeleton features and intravascular fault patterns, we performed animation of vertical structure along the cardiac cycle by applying the Q criterion to velocity data. We can appreciate the presence of contraction and expansion regions of washer stress and the washer stress fixed point on the luminal surface where the rotating blood flow structure interact with the wall. Moreover, we can color the vertical structure by the distance from the luminal surface to more appreciate the rotating blood flow structure near the wall. The flow topology is similar to all models, and we can note that the flow is characterized by a courgette that rolls up into a large vortex ring entering the aneurysm sac, and then this vortex ring dissipates in the proximal part of the sac of the aneurysm. So the dynamics of this vortex ring could have important biomechanics implications, since experimental and numerical studies have shown that thrombus formation may be driven by platelet activation and aggregation within the recirculation zone. For this region, here we show the extraction of vortex ring at different time steps along the cardiac cycle in order to reconstruct the dynamic of the vortex ring. Finally, based on the well-established significance of helical flow, inducing flow stability and reducing flow disturbance, intravascular blood flow patterns were here visualized by using the local normalized velocity to indicate the direction of the rotation of helical blood flow patterns. If the local normalized helicity is positive, the helical fold structure are right-handed, while if local normalized helicity is negative, the helical flow structure are left-handed. From the results, we can observe the organization of blood flow in two balanced contra-rotating helical structure in the model 2, 6, and 8, presenting a physiological blood canalization, while we can observe a more chaotic blood flow structure inside the aneurysm sac.
Okay, to conclude, we wanted to show you a possible future development of this study. Very recently, we developed another advanced tool for hemodynamic characterization, motivated by the need to disentangle the complexity of 4D hemodynamic flows and to provide a robust quantitative definition to the so-called coherent hemodynamic structures, which are those structures where a fundamental hemodynamic quantity shows a significant correlation over a range of space and or time. So we wanted to know how this hemodynamic correlation, for example, between blood velocity signals propagate inside an artery. And in order to answer to this question, the basic idea was to model arterial flows as social networks, using in particular the theory of complex networks to capture how correlated four-dimensional blood flow patterns evolve and propagate in space and time. This methodology using complex networks has already been applied in recent studies from our team. For example, we used complex networks to characterize hemodynamics in personalized CFD models of carotid bifurcation and also coronary arteries. And very recently, we also extended the complex networks approach to a 4D flow MRI in vivo study of dilated human ascending aortas. And this study showed the potential of the complex networks approach to provide indicators for a final risk stratification of ascending aorta disease to be used potentially in a clinical framework. So we tried to apply the complex networks approach also to study hemodynamics in abdominal aortic aneurysms. And here I will be very briefly show you how these complex networks are built starting from cardiovascular data. So first of all, CFD data are used to extract the time histories along the cardiac cycle of a specific hemodynamic quantity, usually velocity-based, defined at each node of the computational mesh. Then a correlation criterion is used to build the complex networks, which are made up of nodes and links between nodes. In particular, the nodes are represented by the time histories of the specific investigated quantity at each grid point. And if the correlation coefficient between two time histories is greater than a specific correlation threshold, then a link, a topological link, is established between the two nodes. Otherwise, if the correlation between the two time histories is below the chosen threshold, then no link is established between the corresponding nodes. So in this way, we obtain a sort of a spatial network whose topological structure, which is basically the pattern of connections between the nodes, provides useful information on the organization of hemodynamic flows. And so a series of complex networks metrics have been proposed to retrieve such information. So for example, we can compute the degree centrality, which measures the degree of dynamical similarity of hemodynamic flows by simply counting the number of connections, which are called the neighbors, of each node inside the networks. We can also measure the distance of each node from all its connections, from all its neighbors, by computing the so-called average Euclidean distance metric, which allows for the first time to quantify the anatomical persistence length of the correlation inside an arterial district. And so these are just preliminary results on abdominal aortic aneurysms, and we noticed, interestingly, that, for example, the nodes of the network with the fewest number of connections, and also for which the dynamical correlation expires in a short distance, are located inside the aneurysmatic sac. And so this could be, it could be interesting to further explore also the complex networks approach in relation to the aneurysmal flow. So in conclusion, we saw that patient-specific blood flow modeling is a promising tool that may provide useful insight for understanding the hemodynamic factors which are directly involved in the aneurysmatic disease progression. And so we presented a framework combining patient-specific CFD and advanced fluid mechanics tools of analysis to study the hemodynamics in the abdominal aortic aneurysms. And the use of the presented approach in prospective and longitudinal studies could contribute to increase the chance of finding a mechanistic explanations of to the clinical observations, and ultimately to provide potential clinical markers for rupture risk prediction. As next steps, it could be useful, for example, to improve the hemodynamic characterization by using personalized patient-specific boundary conditions, and also, for example, by considering the full abdominal aortic aneurysm model, so including, for example, the iliac bifurcation. And as an ongoing step, we are starting to apply the presented approach on a very much larger data set of virtual abdominal aortic aneurysm patients, which are the ones generated by Ludovica, that she showed us in her presentation, which are, as we have seen, characterized by different geometric features. And so with that, we would like to thank all of you for your attention.
Thanks a lot, Karol and Valentina. Thanks for this nice and inspiring talk. Any questions? I can start with a question, maybe. If you can go back just to slide 31, it's concerning the last approach that you were talking about. It's the correlation-based complex network. It's so
31.
31, yes, thanks. Yeah, it's a very simple question. It's nothing. The question is the following. So here you check the space correlation and see if two signals are correlated, then you create a link, and if not, there's no link. Okay, very often in fluid mechanics, people look at shifted in time correlations. Is this anything that can be interesting for you? Meaning, when you do the check, you can check if 2 points are correlated after a certain time, in the sense that this coherent structure might have traveled, for example, downstream, and then you'll find the correlation after given delta t. Is there anything like this in the literature or in any interest in this direction?
Yes, actually, there is the literature is there are studies that check for some correlation considering the delay, so the phase shift, and there are so the theory of complex networks is a wide branch of is based on graph theory. So there are a lot of criteria that can be used to build the networks. So in our case, we use, as I said, a correlation criterion that basically correlates the shape of a time series data. But there are also cases in which we can for sure correlate some, for example, behavior considering, yes, the shifting in time. This application is the first of complex networks, is the first application in cardiovascular data. So there is nothing in the literature regarding the specific biomedical application, but in other fields, for sure, there are, and it is actually something that we can also explore in cardiovascular data. And I think it would be useful, for example, if we consider in our simulation maybe also the wall motion, because we usually model blood flow using the assumption of rigid wall. But maybe considering also taking into consideration, for example, wall motion, wall distensibility, it could also be useful to consider, for example, the shifting in time during the cardiac cycle of the temporal behavior of a certain signal.
Thanks.
Thank you.
Additional questions?
Anyway, Angelo, the phase shift is implicitly included in the analysis because the correlation coefficient give you an indirect, direct or not direct measure of how much to velocity waveforms are shifted in time or not. By the way, it's not direct, but you have a feedback from the complex network analysis on this.
Sure.
If you have a rigid model, this is not so relevant. What we do in general, at the moment, we are testing the correlation with respect to the flow rate waveform of each node of the network, for example, because this is something, because we have a physical quantity that driving the flow. So the inlet flow rate waveform is the forcing term. So the distance in terms of correlation for the flow rate give you a measure of the disruption of the correlation inside the fluid domain.
Okay. Okay. Thanks. Any additional question? So I don't want to monopolize the questions, but just to recall what is the plan of our collaboration. If you go back to, again, to figure, I mean, to slide 21 or 22, any of them, it's fine.
Okay.
Yeah, so 21, yes, or 22. So the plan would be the following. The plan is that relative to the question that Umberto posed Ludovica half an hour ago, basically, the idea is that once we get the, let's say, the encoded values, so the latent variables, okay, for each of those aneurysms, the plan is to get the surface plot that we are seeing here directly in as a function that has been learned by a database. So that's the plan, basically, which could be a decision-making tool for a clinician. Now, how the clinician could use this data, that's another story. Okay. So I think you are muted, Umberto.
I perfectly agree. The nice part of the story, the sad part of the story is that we don't know exactly which hemodynamic descriptor better identifies or better predict the outcome of a triple E. But for example, we have some feedback at the moment from more simple geometries, stenotic coronary vessels, and some of these descriptors, in particular this one, the TSVI, we recently demonstrated that it is a strong predictor of myocardial infarction, but the coronary arteries is a completely different hemodynamics. I have no idea at the moment if this predictor, for example, or another one is sufficient to predict, robustly predict the outcome of an aneurysm in patients. This is something that has to be tested, and the parameterization, in my opinion, is a very strong, could be a very strong approach, a robust approach to identify or clarify if the hemodynamic way is helpful to predict the evolution of the pathology.
Okay, thank you, Umberto. I think, are there additional remarks?
I have a question.
Please.
I want to know if you, in your model, do you think that not using the interaction fluid structure has a significant impact on the veracity of the results, or this interaction is negligible?
Okay, so in our simulations, we do not take into consideration wall motion. So we may just make the assumption of rigid wall. I think that it depends on the single cases. For example, maybe there are cases in which the intraluminal thrombus may be, for example, play as a sort of protection of the vessel lumen, and so it may let's say reduce the motion, wall motion, and maybe in this case the assumption of rigid wall may be more reasonable than other cases. But taking into consideration an FSI simulation means also introducing other uncertainties, because of course you have to make assumptions on wall materials, wall property materials, and so on. The rigid wall assumption is the most largely used when studying, for example, abdominal aneurysm flows.
Thank you.
If there's time, I would have a question.
Hi, Sam.
Let's say regarding the big picture that that you depicted, Angelo, together with the work of Ludovica and of Karol and Valentina. So there's one thing that maybe I missed it. I mean, I don't know, these computational models, I mean, how heavy they are. I mean, I imagine, I mean, that on any infrastructure they may run overnight, right?
Okay.
I don't think.
So, yes, we can give you an idea. For example, one single model of the dataset that we processed takes around
2 days.
2 days to simulate 6 cardiac cycles on a computer machine using 24 threads.
Okay. So, I mean, just working on IT, we could, I imagine, that we could come around with simulation times of the order of hours.
Exactly, yeah.
Is there really the need of, I mean, if the model was reliable in order to take a decision, is there really a need to put into the place all the stuff about parameterization, reduced order models? I mean, it is just one computation for a given patient.
That's a reasonable question. The fact is that the surgeon, before going to surgery, but Florian can be more precise, has something like 5 to 10 minutes to look at the patient. So there is simply not the time to wait for a couple of hours or this kind of time. But also the infrastructure that is needed is different. That's part of the question, the answer. And the other part is that, in a sense, you can imagine that you have this kind of crawlers that crawl into a database and look for dangerous aneurysms that are undetected in the scans of hundreds of patients that are stored in a hospital database. But please, Florian.
Yeah, maybe it's more a question of clinical workflow for physicians than pure how much time do we have to take the decision. So yeah, it's more a question of integration into the clinical workflow. I mean, today, if you come with a solution and you say to the radiologist or the surgeon, once you get the image, you'll have to wait for 1 day or a few hours to get the results. For them, it's too much. So they won't take the solution. It's pure question of integration and implementation into clinical workflow. And yes, then all the infrastructure you need to put in place is even more complicated because you don't have any big HPC servers in an hospital. So it means that you need to sell that too. But it's not a scientific question, I would say. It's more for the business point of view.
Yeah.
Just to answer to your question, we have recently an experience with collaboration with cardiologists in trying to using simulations to extract some mechanical biomechanical marker of future disease in stenotic coronary arteries, and they are interested in the washer stress evaluation of washer stress based descriptor analysis only if you are able to assure them that they can obtain the washer stress number in 15 minutes, 20 minutes. This is interesting, of real interest. In particular, if you have already demonstrated that this is a strong biomechanical predictor of something. But this is not sufficient, as Florian said. They must have the number, the magic number, in no more than 20 minutes. Otherwise, they go out of their clinical workflow, and it makes no sense to them to use the number.
Okay.
Great. So let's see. By the way, to do a simulation, you still, to do the simulation automatically, you still need some, let's say, advanced tools that are able to isolate the aneurysm out of the whole segmentation to make the grid and whatever. So also there, it's not completely transparent, let's say. Okay, so great. Thanks all for the discussion, and we